understand them and use them in different ways. So we are looking forward to developing that relationship. Tonight, I'm pleased to have Dr. Gerald Schieven talk to us. He's going to tell us about the cold universe with a telescope called ALMA in the Atacama Desert in Chile. Dr. Schieven is originally from Ontario and got his PhD at the University of Massachusetts Amherst and worked at Queen's, NASA JPL, in this place called the Dominion Radio Astrophysical Observatory.
DRAO is in Penticton.
Yeah, right. I'm kidding. Also run out of this place and worked at the James Maxwell Telescope in Hawaii and has been here since 2008 and has not outstayed his welcome quite yet. In his spare time, I've worked with Gerald for a donation to the Pacific Opera Victoria, which he's obviously also very passionate about.
Yeah, we just finished a production of Rigoletto, which was a lot of fun.
So, without further ado, and without wasting any of your time, here he is.
Thanks, Ben. Hi, everybody. Now that you know who I am, let's just delve right into our talk. When you think about astronomy, what do you think about? Go outside at night and look up, and what do you see? Stars. But let me ask a question. Why can you see stars? They're bright. Why are they bright? They're emitting light. Why are they emitting light? They're not burning. They're not burning. But they are they're very hot. Stars are hot. Hot things give off visible light. Your eyes are sensitive to visible light, so you can see stars because they're hot. But there's a lot of stuff out there that is not hot. But where did my picture go? Come back, come back. Yeah, well, it's not quite St. Patrick's Day, but there, we're back. Okay. Okay, we're back. But here we have we're looking at a picture of the Milky Way galaxy. If you've ever been to a nice dark sky, especially in the summertime, you'll see this hazy patch of light extending across the sky that we call the Milky Way. The Milky Way is actually, we'll see pictures of what galaxies are, but the Milky Way is just full of stars, hundreds of billions of stars. It looks like a big flat pancake, and we live inside the pancake. So that when you look up in the sky, you see this band of hazy light across the sky. But if you use a small telescope, you can see they're all individual stars, hundreds and thousands of stars. But there's a lot of stuff in here that is not stars, black stuff, it's dark stuff. These are not holes. We're not looking through where there aren't any stars. There's a lot of stuff here, but it's not giving off visible light. Now, lots of people are familiar with well, everybody is familiar with visible light, I hope, and the telescopes that we use to study visible light. There's this one, for instance. I hope you've had a chance to go to tour the observatory. If you haven't, after the talk, definitely go in and have a look. This telescope is now over 100 years old, but it's still being used for science. There are smaller telescopes and larger telescopes up on top of mountains like these here up in Hawaii. This one is in Quebec, and this one I brought with me when we went to watch the eclipse in 2017. But these are all optical telescopes that are designed to detect visible light. They're like gigantic eyes. You want big eyes to study the stars because these big eyes, these big telescopes with lots and lots with great big mirrors will detect very, very, very faint light. So the telescopes are really used to look not far away, but to look at faint things. But again, what do we do about the stuff in between the stars that doesn't seem to be giving off any light? The reason it's not giving off any visible light is because this stuff is mostly very, very cold. And let's do a little experiment. Think of an old electric stove, not these fancy, nice induction stoves, the old-fashioned kind where you turn the element on and it gets very, very hot. The electricity passes through the coil. It gets very hot, and when it gets very hot, it starts to glow, and it glows in visible light. Then turn the element off. What happens? It dulls. It's no longer giving off visible light. Is it giving off any kind of light? Oh, yes, it is. It is giving off what we call infrared. It's not giving off visible light anymore, but it's giving off lots of infrared. So things that are very warm, but not really hot, are still giving off light. It's not visible light. They're giving off infrared. Your skin is actually a pretty good detector of infrared, as you might remember if you accidentally stuck your hand on it. But what would happen, though, if we took that element, and an infrared telescope, if you want to detect infrared radiation from warm but not hot stuff, you would want a telescope that was sensitive to infrared radiation. And you can find some telescopes like that are designed for that purpose here on Earth, but there's also the James Webb Space Telescope, which launched about a year or two ago, which has been absolutely fantastic in detecting the infrared light from warm stuff, not quite so cold, or not quite so hot. But suppose we took that stovetop, tossed it into a vat of liquid nitrogen. It's now very cold. It is very cold. It's so cold that it's not giving off any visible light. It's giving off only a very tiny amount of infrared. But it is still giving off radiation. It's still giving off some forms of light that is, we tend to call it microwaves or radio waves. So if you want to look at cold stuff out in space, you'd need to have a telescope that was designed to detect these microwaves, these radio waves. I have to remember this is not my... So visible light is only a very tiny fraction of the whole range of electromagnetic radiation that exists. It's only a very tiny section of it. We are sensitive to it. Our skin is sensitive to infrared. Our skin is also sensitive to ultraviolet, but we try to prevent ourselves from getting that ultraviolet because it gives us a bad sunburn. But ultraviolet, X-rays, gamma rays, those are all generated by things that are super hot, incredibly hot. Things that are warm generate infrared, and things that are cold generate these microwaves. So what would we use? We would want to have a telescope that was specifically designed to detect this cold stuff. And a telescope doesn't look like your typical backyard reflecting telescope, or like the ones that they have out on the patio out here. They look more like big satellite dishes, big radio satellite dishes. This is a submillimetre telescope, a telescope designed to detect microwaves. It is built in Hawaii. It's called the James Clerk Maxwell Telescope. And when it was built, it was a part partnership between England, Holland, and Canada to build this telescope for quite a long time. This was the largest telescope in the world designed to detect the cold gas and dust in between the stars. All that dark stuff that we saw in the picture before, earlier picture. It's also built in Hawaii, and here it is way over here. These are all optical telescopes, and there's this small submillimetre telescope here on Mauna Kea. The reason you want to build it on top of very tall mountains like in Hawaii is that microwaves, I'm going to call them millimeter waves or submillimeter waves because that's the wavelength of the radiation. But it's also microwaves or radio waves and so on. The reason that we want to build them on top of these very, very tall mountains is because they're extremely sensitive to water vapor. Well, there's something in your kitchen that tells you that, yeah, you don't want to have a lot of water vapor when trying to detect these things. A microwave oven works by beaming these microwaves into the water in whatever it is that you're trying to cook. And the water molecules will absorb that microwave radiation. It makes the water molecules start to spin and bump into each other, and this makes them bump into each other and start moving really fast. And that is what causes heat, and that's what cooks your food in a microwave. Well, it works the other direction too. Suppose you've got these microwaves coming from space. They come through the atmosphere. Anytime they hit a water molecule, the water molecule will absorb that microwave, and it'll make the water molecule heat up. So if there's a lot of water in the air, like down here at sea level, the microwaves simply don't get down to the ground. You need to have the telescope above almost all the water. And places here like Mauna Kea in Hawaii are up at about 4,000 meters elevation, and they're extremely dry. There's very little water vapor above them, as you would probably notice if you were up there and your throat getting dried out from all of the dryness. There are only a few places on Earth that are really suitable for building telescopes like this. Hawaii is one of them. Well, that's nice. Who cares? So we can detect microwaves from outer space. Big deal. Why is that important? Well, as we noticed, that whole patch of sky is completely dark. You cannot see it. It does not give off visible light. If you had an infrared telescope pointing at those clouds, then you might actually see stuff that you wouldn't see with an optical telescope. But what you're mostly seeing are young stars buried inside these clouds that are recently born, and so you can study the young stars as they're being born inside these clouds with an infrared telescope. But if you want to learn about the gas and the dust itself, you need a submillimeter telescope. You need a microwave telescope, like the James Clerk Maxwell telescope. So what we can do? We can study cold dust and molecules. We learn where the material is. There's actually a lot of it out there. About half the mass of the galaxy, about half the matter in the galaxy is this cold gas and dust that we need these telescopes to see. You can tell where the material is, how much there is, what it's made out of, how it's moving, what temperature it has, chemistry that goes on. There's a lot of molecules, a lot of very smelly molecules out there. And the chemistry can actually tell you something about the conditions that are occurring in these clouds and how the gas and the dust are what's happening in them. One thing that's really cool is that inside these giant gas clouds, if they become large enough and if they become unstable, they can start to collapse and form new stars. So it's out of these gas clouds that we see that are just dark in visible light. we're getting new stars being formed all the time. That's my favorite, my specialty was studying star and planet formation. So that's why I was so interested in all this. Well, let's just see what it might look like if we were to use a microwave telescope, a submillimetre telescope, to study some of this gas in the dust. Well, here's an optical picture. What is this a picture of? It's Orion. There's Betelgeuse. I'll only say it once. It's a giant red star. It's very old, and it's probably going to blow up in the next million years or so. There's Rigel, Bellatrix. One of these is anyway. There's the three stars that form the belt. Then there's the stars down below that form the sword. But there's this fuzzy blob right here in the middle. Let's take a little closer picture, a look at that. There's this is a nice picture taken with long exposure with a big camera of the Orion. Again, there's the three stars in the belt. There's Betelgeuse. Whoops, that's twice. I won't say it again. Then there was all this bright red stuff. This is gas that has been heated up by these very bright stars here in the belt and down here in the sword. If the gas has been heated up, then you can see it with an optical telescope. But let's look a little bit further down here into this region. There's a close-up picture of it. Now it looks really quite cool. If you look carefully, there are a bunch of very, very hot young stars in here that are heating up the gas and the dust around it. They've blown this giant bubble right here. And here you're seeing the walls of the bubble. And all through here, you're seeing all kinds of filaments, all kinds of gas and dust that's cold. And so you're not seeing it. If we use an infrared telescope, you can start seeing the hundreds and thousands of stars that are within these clouds that are recently born stars. So all of these stars in here are all quite young. Were born within the last million years or so, probably even more recently than that. But if we use something like the James Clerk Maxwell telescope, then that whole region looks like, whoops, go back, too fast. Doink. There we are. Now we are seeing the gas and the dust itself. There's this huge filament. This gas right here is toward those really hot bright stars that we saw. This area is the Orion Nebula. But there's all this stuff down here that we do not see at all. But now you can start seeing it with the JCMT, and you can start measuring how much material there is, how fast it's moving. You can measure the motions of the gas. You can measure the temperature, the composition, and so on. We also have been using it to study the debris disks around young stars. A debris disk is when is from comets around a star that are colliding. They collide together. They break apart, and they form a huge ring of dust around a young star. This is a drawing of one that of this object called Epsilon Eridani. I was actually involved in this project. We were the first ones to map this star. This is a young star. Right in the middle here is a young star. You don't see it in this image, except for somebody drew it there. But all this stuff around it is dust created by colliding comets. Now, this was the first time that we'd seen anything like that. And the cool thing was that what we were able to determine was that this has the equivalent of the last few years you've seen a couple, maybe 3 or 4 comets that have appeared in the sky. There was one just recently that had was quite nice in the evening sky. I forget the name of it. What's that? Sorry? NYRID? No, it wasn't that one. But that's not the one I remember anyway, but that one might have been. Anyway, you might get a comet every few years, a comet every 2 or 3 years or so. This one you would see about 10 comets in the sky at all times. There are so many comets that are all colliding and forming this dust ring around it. We also study galaxies, distant galaxies, and the JCMT studied a section of the sky where they weren't expecting to see anything, and they ended up with an image that looked like this. It's got to be the most boring image that you can possibly imagine. But each one of these dots on this map is a galaxy that had not been seen before and had so much gas and dust in it that we knew that these galaxies are very far away, and this is showing us evidence for the time when galaxies were forming their stars. These submillimeter galaxies were discovered by the JCMT, and they changed our understanding of how the universe evolved. So that's just a few things that we discovered with the JCMT. I mentioned the JCMT because I worked there for 13 years, and it was a wonderful place to work. I loved working in Hawaii. I like living here, though. I don't think I want to move back to Hawaii anytime soon. But fine, we had the JCMT. We made all these important discoveries. Why do we need bigger telescopes? Why do we need better telescopes? Well, I mentioned about optical telescopes. You like big telescopes because they can detect really, really faint things. Well, same thing with millimeter wave telescopes, with microwave telescopes. We want big telescopes because they are very, very, very sensitive. They can detect extremely faint stuff. But there's another reason that we really want it. It's not just the sensitivity, but we also would like resolution. What do I mean by that? Well, the resolution of a telescope, how fine an object you can see with it, depends on the diameter of the antenna or of the mirror. If you have a small telescope, well, suppose we wanted to look at this. Let's pretend this is a section of the sky. We have a small telescope. The telescope can see nice faint stuff, but it does not see very high resolution. It's very, very, very low resolution. It only can see big blobs. So if you look at this tiny telescope looks at this, it can see, oh, there's material there. There's material that looks like kind of filamenty. It's got some blobs here, some interesting structure, but you might be able to use it to tell, well, how much material there is, but it's hard to tell what it actually is. Well, let's build a bigger telescope. Well, now you can see some more interesting structure going on here, but we still don't see exactly what it is, but you can certainly see that there's a lot more interesting structure, and you may want to model what's going on. But again, we want to see what these individual things are. We would like to build a really big telescope, and all of a sudden, we're seeing cherry blossoms at night. Well, that's fine. So what we need to do is to build a big telescope. The James Clerk Maxwell telescope was a big telescope. It had a mirror that was 15 meters in diameter. So it was, we call it a 15-meter telescope, diameter telescope. It was able to see things. It would have been, if it had been used to map the moon, you'd be able to see some of the big craters, some of the big dark patches that you see on the moon. but it wouldn't be able to see, you wouldn't be able to distinguish any of the craters or anything like that. So if we wanted to, say, study how the gas and the dust around young stars in detail, in order to find out maybe how planets are being born inside these clouds around stars, then we wouldn't want to have a telescope that is only 15 meters in diameter. It'd be nice to have one that's 150 meters in diameter, 300 meters in diameter, 2 kilometers in diameter, 15 kilometers in diameter, in order to see things in really fine detail. But I don't think that it's very practical to try and build a telescope that is 15 kilometers in diameter. You might be able to build one that's 100 meters in diameter. There are plans to build a 100-meter diameter optical telescope, although they're very distant plans. The biggest telescopes right now are of order 100 meters. The biggest single-dish telescopes are of order 100 meters. But if you want to build them kilometers in diameter, you just can't do it. But there's a trick that makes it possible to build telescopes that big, and that's that you don't need to have a whole single dish. You can just have pieces. So instead of one giant dish, we just have lots and lots and lots of small dishes that are all scattered around the area that we would have for the big dish. So a telescope that was made out of lots of antennas here could be made to work together as if they were one enormous telescope. And that's what was done with the Atacama Large Millimetre Submillimetre Array. So instead of building a 15-meter telescope, we now have 66 antennas built in northern Chile on a plain about 5,000 meters in elevation. This is an early picture. All the antennas seem to be pointing in different directions. I should find a better picture than this one. But they all point in the same direction. But this is a very large and very costly project, too big for one country to build. And so the ALMA consortium was put together. It's a consortium of North America, which includes the US and Canada, and Taiwan for some reason. Europe, through the European Southern Observatory Consortium. East Asia, which includes Japan, again, Taiwan, and Korea. And then in collaboration with Chile, because it is built in Chile. It's built at 5,000 meter elevation in a site here in northern Chile. There's right up here, Santiago is about halfway down the country. Chile is an interesting country. It is just literally, it's just about 1 to 200 kilometers wide, but it's about a couple of thousand kilometers long. It is really long and narrow, just on the edge of the Andes. And up here is the Atacama Desert, one of the driest places on Earth. So it's 66 telescopes working together as if they were one giant telescope. But the nice thing about them being individual antennas is that you can pick them up and move them if you want to. So you can have them all bunched together in an array about 200 meters across, or you can move them way apart so that they are up to 16 kilometers apart. Here's a picture. This is probably a better picture. I should just use this one. Here, at least they're looking more or less all in the same direction. There's a control facility up at the top where the correlators are, and they do maintenance and so on. If you want to be up there, though, you have to wear oxygen because it's just there's so little oxygen up there. Here is the compact array where all the antennas are bunched together so that they're only about 200, 250 meters apart maximum. But you can also pick them up and move them and scatter them all across this huge plateau here up at the 5,000 meters in the Atacama. You can see how dry it is. There's not a blade of grass. There's nothing. There's absolutely nothing up here growing. And you can pick them up and move them with this transport vehicle. They have two of them, Lori and Otto. There's the name. This one's Lori. They have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 16. They got 32 independently driven wheels. Each wheel has its own motor, and this transporter will back up to the antenna, lower itself a little bit, slip it under the antenna, and pick it up, and then pull it right up to the back of this transporter. There's the guy. There's the little chair for the where the driver sits. The nice thing about this, it has power and keeps the telescope operational and cold. All the receivers way up here, all the receivers are kept at a very, very low temperature, about 4 degrees above absolute zero. They have to be very cold because we're detecting cold stuff. You want your detector to be colder than the stuff you're trying to detect. So it's at about 4 degrees above absolute zero. And of course, if you pull the plug on it, it's going to start warming up. So they make sure that they're plugged in even when they pick up the antennas and move them from place to place. I happened to catch this transporter as it was bringing one down to the mid-level facility in order to do some maintenance on it. I don't get to go up to the summit very often. I did about a year ago. This is my one and only chance to visit the summit. You see I'm wearing got my oxygen on with the antennas in the background. It was quite exciting. At 5,000 meters, there's the oxygen is down, James, what is it?
40%.
It's about 40%. So it's about 40% sea level oxygen. It's, you notice it right away. Now, most people, when they go to ALMA, they don't go up to the summit. In fact, they are very strict about people who go up to the summit. Every time you go up, you have to have a physical, and they check your blood pressure. And the reason they wouldn't let me up is because my blood pressure was always too high. And finally, the day they did let me go up, the employee who was going to be driving us up, he failed the test, so we had to find another driver. Well, that's at 5,000 meters. At about 3,700 meter elevation, there is the operational support facility. That's the OSF. And this is an older picture of the OSF. This is where they built all the antennas before they moved them up to the high site. These are labs and testing facilities, and also where the offices are for controlling the telescope. You run the telescope from here. You can also run it from Santiago. There are residences over here. There's a new residence right over here, which is not in this picture. There's also a sport facility over here. People lived there half of their lives. Most of the employees spend a week there, and then a week off, and then a week there, and a week off. So they live half their lives here. So it's really nice that when they built the new residencia, they put in a swimming pool. That was nice. And they built a sport facility and so on. So it makes it actually comfortable to be there. Otherwise, it is extremely dry. It is an international facility, and when they have VIPs, they bring up all the flags and show off all the flags of all the partner countries, and then as soon as the VIPs have done their tour, they take them all down again, so I managed to catch a very brief period. And here's the control room. At least it's the old control room. Apparently now they have just finished building a brand new control room, so I can't wait to see that when I go back down in. But you can see there's the astronomer on duty over here. I'm not sure why there are so many other people, but this is my training sessions, which is why I have two astronomers here. So I was running the telescope over here with these five 5 monitors over here. The telescope operator was over here. He's monitoring the observatory, making sure everything runs. The astronomer on duty is actually taking observations and doing the calibrations and so on. But there were also not just people up at the observatory. These are some of the residents. The little burrito. I always find that interesting. Why is that food called a little burro, a little donkey? A burrito. But there are other creatures there as well that I've seen while I've wandered around. The Andean condor. There's this is what we saw when Chantal came up there. This is an Andean fox. This is something called a vizcacha. It looks like a rabbit, but look at the tail. Kind of chinchilla. And flamingos, wild ones, not just plastic. And of course, llamas. These are wild llamas. They're vicuña. There are several kinds of wild llamas in Chile, and the ones up in the northern area where the telescope are generally these ones, the vicuña. Just a closer up picture. I like to go hiking around when they allow me, and I was climbing down into one of these into a little canyon and came face to face. Turned around a corner and came face to face with one of the vizcacha. It was literally from me to you. So let me take a picture of it. Just absolutely delightful things. Okay, so we've got ALMA. ALMA's now been in operation for a little over 10 years or so. And it has made some absolutely astonishing discoveries. I'll just show just a very small number because we're about out of time. But some of the more famous ones might be fun to show. One of them is this object right here. Instead of showing just a blob, this is actually a young star called H.L. Tauri. This picture was taken with the ALMA Observatory when it was in its most extended configuration, so it has its finest resolution. But when this image came out about 10 years ago or so now, it's almost 10 years ago, it was absolutely jaw-dropping. It literally changed our understanding of how planets form around stars. This is around a very young star. The star is here in the middle, but you're not quite seeing it. What you're seeing are dust around the star, all in orbit around the star. But you notice also these gaps. They believe that what's happening here is that the dust in orbit around the star is now colliding and collecting and forming bigger and bigger and bigger objects called planetesimals. And these planetesimals are coalescing into larger objects. And when they get to be large enough, they will actually clear out these orbits. And so what we're here looking at is planets being born. Here's another object similar to H.L. Tau, something microscopy. What is it? AUMIC. Yeah. With a very close inset showing the right in the middle of you are actually seeing the star here, and there's a big gap around the star. And this is a drawing of an artist's rendition of what that really might look like if you were able to get really close to it. You can see the star in the middle, all kinds of planetesimals, a few planets that are sweeping out these gaps. They've also used the observatory to map the gas clouds in other galaxies. So each of all this red stuff is all carbon monoxide gas. Carbon monoxide is a poison here on Earth, but it's actually a very commonly found gas in the universe. And it's a really good tracer for this very cold gas. So they were using this to understand more about how star-forming clouds form and act in other galaxies. Then there's the big one that came out a couple of years ago. This is a galaxy called M87. It's a big fuzzy blob. It's a much, much bigger galaxy than our own. If you zoom into the middle, you see this strange object, this jet blasting out from the middle of the galaxy. There is a giant 60 million solar mass. I can't remember the exact number. It's a big one anyway.
It's about 60 million solar mass.
Yeah, there's a black hole in the center of this galaxy. It's enormous, and they wanted to be able to observe the black hole in the center of this galaxy, but they realized that they would need a telescope not 16 kilometers in diameter, but about 16,000 kilometers in diameter. Now that it makes a challenge, but there is a way to do that. It's something called, there's a consortium of observatories around the world called the Event Horizon Telescope, located in Chile, the South Pole, Mexico, Arizona, Hawaii, Greenland, and a couple of places in Europe. And by combining the signals from all of these telescopes, you can get one telescope the width of the Earth. And by doing that, they were able to image the black hole at the center of this galaxy, and also the black hole at the center of our own galaxy. What you're seeing here, this donut, the way light bends around these black holes is such that what you're actually seeing here is sort of the stuff on the back side of the black hole that the light has bent. Excuse me. The light has bent around the black hole, and then it points toward us. But to show you just how big this black hole is, this black area here is the shadow of the event horizon. The event horizon, a black hole is something that is so massive and so compact that its escape velocity, let me explain escape velocity. If you go outside here and you wanted to escape from the Earth, you'd have to jump at about 7.5 kilometers per second. If you could jump 7.5 kilometers per second, you would escape from the Earth and not fall down again. One of these black holes, if you wanted to escape from a black hole, you would have to jump faster than the speed of light. And since nothing can travel faster than the speed of light, then nothing can escape, not even light, from this black hole. At a certain distance from whatever is inside, the escape velocity is exactly the speed of light, and that's generally called the event horizon. And this black circle here is the shadow of the event horizon against the material on the back side. And just to show you how big it is, there's the orbit of Pluto. That's where Voyager 1 was at the time that this image was made. So this is the first image that we have of the black hole. Since then, they've been able to publish images of the magnetic field threading this black hole. They've published images of the black hole around our own galaxy, and some really cool stuff. Well, that's just a couple of the things that the ALMA Observatory has discovered. That's only the tiniest tip of the iceberg. If you're really interested, I would suggest going to almaobservatory.org and look up their press releases. They'll have tons of interesting science results. And in fact, just one press release that came out this week. These are images of all different young stars that are forming planets. So I'm going to leave that at this image. And if we got any questions, I'm happy to answer. And we still have a few minutes. Yes?
This was very interesting. Thank you for the talk. The question is actually, how do microwave telescopes avoid interference from the Earth-based signals?
They are not quite, they're not nearly as susceptible as telescopes like the ones that are in Penticton, DRAO. The ones at tens of gigahertz and longer wavelength. It is a worry because as technology advances, they keep building satellites that are at higher and higher and higher and higher frequency. So it is something that we have to raise at. There's a radio frequency conference in Geneva every year, and radio astronomy has a few representatives there, and we have to basically twist the arms of each national delegation that goes there to say, remember, we need the spectrum too. So it is absolutely a concern. Fortunately, not so much at these really high frequencies at the moment.
Thank you.
Yeah.
I just wanted to say, you say the black hole is really big, but it's a few times the size of the solar system, and it's 54 million light years away.
That is also very true. So they're very big, but they are very, 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 very far away, which is why you need these enormous telescopes to see something that small. Yeah?
Would it, now having telescopes in space, like just say 100 of them or something, would that help in any way?
That is one. There is something called, there is a project called Radio Astron, which put one or two satellites in orbit, but that's to work at much lower wavelengths. But I know the Event Horizon Telescope team has been proposing to NASA to build one or two stations in orbit, in very distant orbit,
and it could work together?
And to work together with the Event Horizon Telescope to get much higher. The problem is that they're not going to be enormous telescopes, and so the sensitivity improvement will not be very good. So you still need really, really bright stuff.
Is it limited what you could put out in space, like the size? Is there limits to size?
Cost. Cost. That's the limitation. Yeah.
Fair enough. Okay. Thank you.
Thank you very much for that talk. I just want to say one other thing. If you to 10 o'clock when we have the observing session started, you will have a chance to actually see M87. It's the first on our target for tonight. Plus, and you can see the jet with this telescope here. Plus, we will also image some of the other galaxies Gerald has shown us. If the clouds stay away, that is. No telescope, however big, can see through clouds, unfortunately, except one of those.
Except the long wavelength. The VLA can look through it, but not ours can't.
Yeah. All right.
Thank you.
Thank you very much for coming.